Well, I think these pictures are spectacular. They're breathtaking. And you realize there's a whole universe out there that we have not seen.
When NASA launched the James Webb Space Telescope into space, its goal was to shed light on the wonders of the universe, and it's delivering on that promise. Since the summer, we've had a steady stream of stunning images of dying stars, distant planets, and colliding galaxies. Scientists expected the telescope's data would support the Big Bang Theory. But ironically, the discoveries of NASA's $10 billion gamble were beyond their wildest dreams, as it captured images so far back in time, revealing the existence of galaxies so old that the very origins of the universe have instead been called into question. Even the renowned physicist Michio Kaku also had to admit that Webb's discovery could upend the current understanding of the early universe.
We may have to revise our theory of the creation of the universe.
Join us as we unveil the mysteries of universe breakers and delve into the awe-inspiring revelations brought to light by the James Webb Telescope. One might say JWST's observations of early galaxies have been billions of years in the making, but more modestly, they trace back to the Space Telescope Science Institute, STSCI, in 1985. At the time, the Hubble Space Telescope was still 5 years away from launching on a space shuttle. But Garth Illingworth, then deputy director of STSCI, was surprised one day when his boss, then director Riccardo Giacconi, who died in 2018, asked him to start thinking about what would come after Hubble much farther down the road. "I protested, saying we've got more than enough to do on Hubble," Illingworth recalls. But Giacconi was insistent. "Trust me, it'll take a long time," he said. So Illingworth and a handful of others got to work, drawing up concept ideas for what became known as the Next Generation Space Telescope, NGST, later renamed JWST after a former NASA administrator. Hubble would be transformational, but astronomers knew its capabilities would be limited by its observations in visible light. As light from a very distant galaxy travels across the cosmic abyss, it is stretched by the expansion of the universe, a broadening of wavelengths known as redshift. The higher the redshift value, the more stretching the light has experienced, and thus the more distant its source galaxy. Redshifts for early galaxies are so high that their emitted visible light has stretched into infrared by the time it arrives at our telescopes, which is why Hubble could not see them. The NGST, in contrast, would observe in infrared and would boast a very large and very cold starlight gathering mirror, allowing it to peer much deeper into the universe. Everybody realized that Webb would be the telescope for looking at early galaxies, Illingworth says. That became the primary science goal. And then, after more than 2 decades of labor at a cost of some $10 billion, JWST finally launched on Christmas Day 2021. The telescope reached its deep space destination a month later, where it would endure exhaustive testing to ensure its optimal performance. By July 2022, it was ready to begin its long-awaited first year of science observations, known as Cycle 1. At that time, many thought that extremely distant galaxies were predicted to pop up only after a few cycles of data from multiple programs. Yet, much of the surprise of astronomers, unimaginably distant galaxies shocked astronomers came into view immediately. In a study published in Nature, an international team of researchers reported the detection of light emitted by these galaxies about 13 billion years ago, or to be more precise, 500 to 700 million years after the Big Bang. The age of the galaxies was determined from the red shift of their radiation, a phenomenon in which the length of electromagnetic waves increases along with the expansion of the universe, similar to the Doppler effect. Comparing the light wavelengths with what they expected from the radiation of real galaxies allows astronomers to figure out how long the light took to travel to get to Earth, and hence how old the object it emitted is. By analyzing the light intensity and spectrum, the scientists were able to deduce the masses of the galaxies and concluded that they are almost as large as our own Milky Way. But such behemoths emerging so rapidly defies expectations set by cosmologists' standard model of the universe's evolution, called LCDM, or lambda cold dark matter. This model incorporates scientists' best estimates for the properties of dark energy and dark matter, which collectively act to dominate the emergence of large-scale cosmic structures. To understand the dilemma, a brief refresher is needed. In the first second after the Big Bang, our universe was an almost inconceivably hot and dense soup of primordial particles. Over the next 3 minutes, as the cosmos expanded and cooled, the nuclei of helium and other very light elements began to form. Fast forward 400,000 years, and the universe was cold enough for the first atoms to appear. When the universe was about 100 million years old, theorists say, conditions were finally right for the emergence of the first stars. These giant fireballs of mostly hydrogen and helium were uncontaminated by heavier elements found in modern-day stars, so they possessed significantly different properties. Larger and brighter than today's stars, these first suns coalesced in proto-galaxies, clusters of gas that clung to vast, invisible scaffolds of dark matter. Gravity guided subsequent interactions between these proto-galaxies, which eventually merged to form larger galaxies. This process of becoming, of the early universe's chaos giving way to the more orderly cosmos we know today, is thought to have taken about 1 billion years. And JWST's discovery of bright galaxies in the early cosmos challenges this model. "It's bananas," said Erica Nelson, assistant professor of astrophysics at CU Boulder and one of the authors of the study, in a press release. "You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. In order for such large galaxies to form so quickly, the rate of star formation in them must have been orders of magnitude higher than what scientists expected." As Nelson explained, the Milky Way forms about 1 to 2 new stars every year. Some of these galaxies would have to be forming hundreds of new stars a year for the entire history of the universe. These findings contradict not only theoretical ideas, but also the data collected by other well-known space observatories, such as the Hubble and Spitzer telescopes, which have previously observed galaxies of about the same age, but much less massive. If true, these results will turn our understanding of the origin and evolution of the universe on its head. However, the researchers note that in order to confidently declare such a sensational discovery defying the whole modern cosmological theory, further observations and data analysis are needed. It is possible that their assumptions about the structure of galaxies and the details of their radiation spectrum are incorrect, and in reality, these galaxies are much lighter than the preliminary study suggests, which will make their masses consistent with theoretical understanding. One other possible explanation for the contradiction is that these galaxies are not what scientists think they are, but new objects that would still be consistent with modern cosmological theory. Another possibility is that these things are a different kind of weird object, such as faint quasars, which would be just as interesting, explained Nelson. Whatever these objects are, further research is likely to have a very serious impact on our theories of the evolution of stars, galaxies, and perhaps the universe as a whole, requiring a significant change in understanding of the processes occurring shortly after the Big Bang. If even one of these galaxies is real, it will push against the limits of our understanding of cosmology, concluded Nelson. Whilst this data from the JWST is about as close as we can get to conclusive evidence proving that the universe was not created in a Big Bang 13.8 billion years ago, some field-leading astronomers now believe we must contrive mechanisms to make galaxies form at absurd, unphysical speeds. Listening to highly esteemed astronomers drawing such conclusions about the need to salvage the Big Bang from the empirical evidence, we are struck by certain parallels between the present situation in cosmology and the state of geology in the 17th century. In the 17th century, the science of geology, like astronomy today, was going through a phase of rapid accumulation of new observational data. Nicholas Steno, a Danish scientist, had noted that some rocks found on mountainsides were identical in form to modern sharks' teeth. How could sharks have lost their teeth on mountainsides? Meanwhile, strange mineralized bones were turning up in deep limestone quarries, fossils of long dead animals, unlike anything presently walking the earth. In his observations of rocky outcrops, Steno also observed clear stratification. Clearly, each stratum had been built up layer upon layer in chronological succession. Steno's observations suggested the Earth has a history, a far richer one than previously suspected. Sharp differences appear at certain points in the rock. Some layers suggested there had once been lush forests, others indicate desert conditions, others riverbeds that long ago dried up. And within those layers, unique fossils that point to whole ecosystems coming and going. How could this rich history be squeezed into the short timescale dictated by the Book of Genesis? That was the problem facing geologists. It is a problem not so dissimilar to that posed before cosmology as we delve into our local universe and its history and find universe-breaking galaxies, just as Steno delved into the Earth's strata and found sharks' teeth. Yet human thinking is conservative by nature, and the creation story of Genesis did not instantly give way before the new evidence. Instead, reality was shoehorned into the theory. Catastrophes were invoked that might have laid down enormous amounts of history in a short time. Meteor impacts, great Noachian floods caused by the Earth passing through comet trails, etc. These were the origins of catastrophism, a theory of cataclysms making and remaking our planet. On the basis of false hypotheses, a great deal of excellent science has been conducted. Many false theories contain a rational kernel that demands to be separated from its false and irrational husk. That was true of catastrophism, which was the theoretical lodestone of a great geological school in France. And although the catastrophist view was eventually forced to yield before the unstoppable advance of empirical science, it is recognized today that the Earth has seen many episodes of catastrophic change. Not only are these periods not in contradiction with the existence of other epochs of slow, gradual change, but the latter laid the basis for the former, and vice versa. Of course, every analogy has its limits, and it goes without saying that cosmology is not geology. Nevertheless, just as what was valuable in catastrophism is preserved in modern geology, so everything of value in the present cosmology will find its place in a higher understanding of the local universe. The idea of rapid periods of structure formation, of one or many Big Bangs in the sense of phases of rapid expansion of parts of the universe, may very valuably inform our understanding of the universe long after the standard model of Big Bang cosmology has been abandoned. But we are convinced that the irrational side of the theory, the idealistic notion of an origin to the universe, of a moment of creation of matter, space, and time, and all the absurd mathematical patch-ups that keep the theory going, all that will be forced to give way under the weight of observational evidence, and scientists will once more recognize that the universe is infinite and eternal, and that matter can neither be created nor destroyed. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. As always, thanks for watching, and we will see you next time.